Application of friction in machines. In section B, we investigate the action of friction in various machine applications. Because the conditions in these applications are normally either limiting static or kinetic friction, we will use the variable mu rather than mu s or mu k. In general. Depending on whether motion is impending or actually occurring, mu can be interpreted as either the static or kinetic coefficient of friction. The first machine that will be discussed is wedges. Wedges. A wedge is one of the simplest and most useful machines. A wedge is used to produce small adjustment in the position of a body or to apply large forces. Wedges largely depend on friction to function. Depends on friction to function. When sliding of a wedge is impending, the resultant force on each sliding surface of the wedge will be induced from the normal to the surface by an amount equal to friction angle. When sliding of a wedge impending, the resultant force on each surface of the wedge will be inclined from the normal to the surface by an amount equal to friction angle. Which is always in the direction to opposed to the motion of the wedge relative to making surface. The motion of the wedge opposed to the direction wedge. This picture shows a wedge used to position or lift a large mass M. Consider this picture. This figure shows a wedge used to position or lift a large mass M, where the vertical loading is mg as shown in the picture. The coefficient of friction for each pair of the surface mu is equals to tangent phi. As shown here in this picture, we have the surface with a normal direction and R applied to this point. Alpha is tangent mu, and theta, let me show with phi. Phi and alpha is here. So if we want to the direction of the continue this line, to the normal, we have this angle is alpha plus phi. So as shown here, for the case R, we have these directions. For the normal, mg for example, R3 as shown in this picture, and R2. R2, we have this angle alpha plus phi. So we can calculate R3 a square, R2 a square, W a square minus 2R2 W cosinus phi plus alpha. Anyway, and the free body diagram for wedge also shown in the picture here. For wedge, we have alpha here and the normal rectangular with R2 to the normal, R2 with phi angle, and R1 also have a same angle here with this surface phi, and a force P here. With making the triangular P R1, for example, with the direction of phi, and R2 with the direction phi plus alpha. R2, R1 and P. We neglect the mass of the wedge. From the free body diagrams, we write the force equilibrium conditions by equating to 0 the sum of force vector acting on each body. The solution of this equation are shown in the free body diagrams, and the triangular law for the forces applied on each part. If P is removed and the wedge remains in place, the equilibrium of wedge requires that the equal reaction of R1 and R2, these two forces, equal reaction R1 and R2 to be collinear as shown in the picture, where the wedge angle alpha is taken to be less than phi. Part A of the figure represents impending slippage at the upper surface, and part C of the figure represents impending slippage at the lower surface. In order for the wedge to slide out of its space, a slippage must occur at both surfaces simultaneously, otherwise the wedge is self-locking, and there is a finite range of possible intermediate angular position of R1 and R2 for which the wedge will be remain in place. This figure illustrates this range and show that simultaneous slippage is not possible if simultaneous slippage is not possible if tangent the angle smaller than the 2 times of the angle of the force resultant force due to friction and normal force. You are encouraged to construct additional diagrams for the case where the alpha greater than phi and verify the wedge is self-locking as long as self-locking. So we can provide a picture for if the wedge is self-locking and is to be withdrawn, a pull P on the wedge will be required. To oppose the new impending motion, the reaction R1 and R2 must act on the opposite side of their normals from those when the wedge was inserted. The solution can be obtained as with the case of raising the load. The free body diagram and the vector polygons for this condition are shown in the pictures here provided here for the various conditions. And for the lower load, the forces Wedge condition, and for the lower load required. The next mechanical machine is the screws.